Okay, hello everyone. Okay. And actually, as announced on the LMS website, and since some students requested the video recordings, excuse me, I posted the previous the video lectures on the YouTube, and I posted the link on the announcement. So actually, you don't have to record this. Actually, the all the video recording will be uploaded on the YouTube website. So I just posted these previous the lectures on the YouTube, and the link was introduced there, so you can just go there to watch the lectures if you want. Okay, but as I announced, if if I observe any decrease in the number of students attending the online class, then I would stop uploading the video lectures. But otherwise, those will be uploaded as you have new lessons. Okay. So, and today's video recording will be uploaded right about 1 or 2 hours after the when the video recording is available. I would download it and upload it to the YouTube. Okay. Anyway, so you can check it. Okay. Anyway, we considered example 9 the other day, and let us consider the next one. So the next one says, given any linear mapping from one vector space to another, the null space or the kernel and the range or the image are subspaces of V and W. Okay, so let us check this. Okay, so to the proof, to clarify the notation, we will use this subscript V and W to denote the zero vectors of V and W respectively. And T is a linear mapping, so zero vector will be mapped to zero vector, meaning meaning zero vector in V is in the null space, and also that also means zero vector in W is one of the vectors in the range. Anyway, this identity shows that the null space includes zero, and so but that is trivial though. But anyway, suppose so for certain subset to be a vector space subspace, we need to prove that for arbitrary pair of vectors, their sum or scalar multiple must be included in the given set. Then the given set will be a vector space, or in other words, it will be a subspace. So let us choose two arbitrary vectors in the null space, say x and y. Now, what does that mean? The null two vectors x and y chosen from the null space. That means, so this means that t will map x to 0 and y will be also mapped to 0. So t of x and t of y will be 0, or 0 sub w in this case, right? So when I consider the image of x plus y, since the t is a linear, I can split this into the sum of these two, and each vector will be the zero vector, so that the x plus y is mapped to 0, right? So we have this x plus y vector under t is 0. What does that mean? That means x plus y is also in the null space. Now, what if I multiply any number, say c, to x? Then the image of cx by the linearity of t can be obtained by multiplying c to the image of x. Since t of x is 0, when you multiply c to the 0, you get 0. Meaning, given this Cx, if you apply t, you get zero vector. That means this Cx is also in the null space, meaning this null space will be a subspace because it is closed on the addition of arbitrary vectors and arbitrary scalar multiple. Okay, so this half shows that the subspace, the null space, is a subspace of the domain. So please remember, the subspace, this null space is a subspace of the domain V. So the null space is a subspace of V. Okay. Now let us consider the image, the range. And as I said, since 0 is mapped to 0, the range already has 0 in it. Now, let us check whether this range is also closed on the addition of arbitrary vectors and scalar multiplication. So let me choose any two arbitrary vectors in the range. Now, in this case, what does that mean? What is the meaning of this? X and Y are chosen from the range. Now, what is the range? The range is the collection of images. So that means, so X and Y were chosen from the image. That means X and Y are the images of some vectors, right? So X and Y are the images of some vectors. Say U and V. In other words, I'm sorry, V and W. Let me follow the textbook. So V and W. So that means there exists a certain V vector such that this V is mapped to X. And there exists another vector W such that W will be mapped to Y. Then X plus V plus W is first of all included in V space because V is closed under the addition, right? So given this, first of all, so here V plus W is some vector included in, I'm sorry, not W, but V space. Because V and W are chosen from V space, right? So this is a some vector in the domain. And when I consider its image, T of V plus W, and similarly, from the linearity of T, we get the sum of these two, and T of V is X, and T of W is Y, right? Then what does that mean? What is the meaning of this? I choose this V and W, okay? And this some, so that is some vector in V, and the image of this V plus W is X and Y. So then what does that mean? X plus Y is the image of V plus W. So T of V plus W equals X plus Y. So that means, so that means X plus Y is the image, is an image of, is the image of V plus W in V space. Meaning this X plus Y is included in the range. In a similar way, if I multiply C to V, it is also a vector in V space, and the image of CV is C times X. So that means this is C times X, CX is included in the range. So when I choose arbitrary vectors X and Y from the range, Their sum is another range, another image, and C times X is also an image of certain vector. So all of T will be a subspace of codomain. So please be careful. So if I consider a linear mapping from V to W, and if this is linear, then I'm considering certain mapping from V to W here. And the null space is a subspace of the domain, and the range or the image is the subspace of the codomain W. Okay, so please be careful. We just considered one subspace from V and W. Now, theorem 2.2 is interesting. Suppose that V and W are some vector spaces and T is a linear mapping from V to W. And here, V1 up to Vn defines a basis for the domain V. Then the range is spanned by the images of T of beta, images of beta, images of the vectors in beta. So let us check this. So our claim is this: the range is spanned by this. So that is the claim. So the claim here we want to prove was the range of this mapping is spanned by T of beta. So that was the claim. So, okay, first of all, the T of each vector in a basis, T of Vi is a vector in the range. And the range is a subspace. So, range contains each vector of T of V1 up to T of Vn, right? And since the range is a subspace, any linear combination of these vectors will be still included in the range, meaning this span of these vectors will be contained in the range. Okay? So this part, the upper three lines imply that the span of T of beta is contained in the range. Okay, so we just considered one direction of the inclusion. Now, let us consider the other direction. So here, let me consider any arbitrary vector from the range. Okay, so that means this W is the image of some vector, say V. And since beta is a basis, any vector in the domain V can be represented as a linear combination of these bases. In other words, even this V, that can be written as a linear combination of the vectors in beta with some coefficients. Now W was the image of V under T, and V is a linear combination of A sub I and Vi. Since T is a linear, I can split this mapping as the sum of these. So that is the sum of T of AI Vi, and AI can be multiplied after you consider T of Vi. So that means any vector in the range can be expressed in this form. In other words, any vector in the range is included in the span of T of beta. So this portion shows that the range is contained in the span of T of beta. So we considered this one and this one up here. So when I combine these two, the conclusion is that the range and the span of T of beta are equal. Right? So, but with this theorem means T of beta will generate any vector in the range. Okay? And this theorem just says that T of beta is a generating set of the range. Then the question is, does this imply that T of beta is a basis for all of T? But in order for a certain set to be a basis, we require two conditions. We have two requirements. One, the set must span the whole space. And secondly, the set must be linearly independent. In this example, in this theorem, the theorem claims that T of beta generates, it spans the range, but this theorem does not imply the linear independence of T of beta. So the answer for the question is definitely no. Please be careful. The theorem just claims that T of beta is a generating set of all of T, nothing more than that. So there are some examples. So let us consider the mapping T from the set of polynomials of degree 2 or less to 2 by 2 matrices. Okay. Then any polynomial in the space will be mapped to this. So for example, if I consider, say, 1 plus x squared, 1 plus x squared, then when I plug in 1 to this polynomial, you get 2. If you plug in 2, you get 5. Their difference is the first row, first column entry. And then you get 0, 0, and f of 0 is 1. So the image of 1 plus x squared under this mapping T will be negative 3, 0, 0, 1 matrix. So anyway, so suppose that I have such mapping. Then we know that this 1x squared is a standard basis for P2 space. So that is the basis of the domain. Then the theorem says the range will be spanned by these three vectors. Now, what is a T of 1? In case of T of 1, it is a constant function. So f of 1 and f of 2 will be both 1. So f1 minus f2 will be 0. And f of 0 is 1. So this matrix is the image of the constant function 1. When f of x is just x, f of 1 is 1, f of 2 is 2, f of 0 is 0. So 1 minus 2 and 0 will go to the diagonal. In case of x squared, f of 1 is 1, f of 2 is 4, so their difference is negative 3, and f of 0 is 0. So all of T is generated by these three matrices. Okay, but note that this third matrix, negative 3, 0, 0, 0 matrix, is 3 times the second matrix. So span of these three matrices will be the same as span of first two matrices. The third one is redundant. I don't need the third one. So the range can be generated by only these two matrices. Now these two matrices are linearly independent because no matter what you multiply to the first matrix, you cannot obtain the second matrix because second matrix has non-negative value in the first row, first column, but the corresponding entry of the first matrix is 0. In a similar way, no matter what you multiply to the second matrix, you cannot obtain the first one because the second matrix has 0 in the second row, second column, but the corresponding entry of the first matrix is 1. So these two matrices are independent. So these two matrices will be a basis. So 0, 0, 0, 1 and negative 1, 0, 0 will form a basis for all of T space. And this basis has two vectors, so the dimension will be 2. Okay. Now, suppose that we want to find a basis for the null space. Okay. So we need to find which vector in the domain is mapped to the 0 vector, right? So we need to find, so for this, we need to find some f of x in the domain such that f of x is mapped to 0. In other words, t of f of x is 0. So we are looking for f of x whose image is 0 vector in this M sub 2 by 2 space. So the 0 vector will be the 0 matrix. And the image of f of x will be defined by this. So the equality implies that the corresponding entries are equal. So that means f1 minus f2 is 0 and f1 minus f2 is 0 and f of 0 is 0. Now our f of x is chosen from the domain. Domain is the set of polynomials of degree 2 or less. So any f of x can be written in this form, a plus bx plus cx squared. Now, this f in the null space must satisfy these two conditions. So f of 1 is the value of the function f when x is 1. So for f of 1, I need to plug in 1 to this f, then you get a plus b plus c. For f of 2, you need to plug in the value 2 in place of x. Then you get a plus 2b plus 4c. Their difference will be negative b minus 3c. So this must be 0. The next equation is the second one. F of 0 must be 0. So if I plug in 0 to this polynomial, you get just a. So a must be 0. So we have two equations. A is 0 and negative b, negative c, negative 3c is 0. So our original function f is defined by a, b, and c, but now if I replace A with 0. And then since negative B minus 3C is 0, if I move this negative B to the other side, then B is negative 3C. So when B is replaced by negative 3C, then you get negative 3cx plus cx squared, that is f. And since both terms have c in common, I can write down c multiple of negative 3x plus x squared. So that means when I consider an arbitrary function f, and then if I assume that the image of f is 0, then this f must be of form some constant multiple of negative 3x plus x squared. That means one basis for the null space will be this set. Okay, so that is a basis for the null space. Now, let V and W be vector spaces, and suppose that T is a linear mapping from V to W, and if N of T and R of T, the kernel and the range, are finite dimensional, then when I say the nullity, this nullity implies, okay, the dimension of the null space. Dimension of the range will be called the rank. Okay, so the nullity and rank are the dimensions of the null space and the range, respectively. The nullity is sometimes denoted by nullity of T, and rank is denoted by rank of T in symbols. So, as I said, T is a mapping from V to W, and the null space of T are mapped to 0, and the range, the R of T, is some subspace of W space, and dimension of the null space is now called nullity, and dimension of the range will be called the rank. Okay, so please remember this. Now, and then we have a very important theorem. Given this linear mapping from V to W, if I add the dimension of the null space with dimension of the rank, the dimension of the range, you get the dimension of what is V? That is the domain of the mapping, not codomain. Okay, so the nullity, and this is the dimension of the range. The dimension of the null space plus the dimension of the range will give you the dimension of the domain, not codomain. Now, since it is a very important and useful theorem, okay, and in this textbook, this theorem is called dimension theorem. In some other books, if you read some other textbooks, then the same theorem may be called rank nullity theorem. Actually, it has different names as well, but anyway, these are two common names of the theorem. Okay, so when you read any paper or textbook, people may say rank nullity theorem or dimension theorem. Then they mean the sum of the nullity and the rank will be the dimension of the domain. Okay? So to prove this, let us consider it. Suppose that dimension of the domain is n, and the null space is a subspace of the domain. So dimension of the null space will be smaller than dimension of the V space, and this is nullity. So nullity will be less than or equal to the dimension of the V space. So let me assume that the dimension of a V is n and the dimension of the null space is k, meaning that is the dimension. Dimension counts the number of vectors in a basis, right? Dimension counts the number of vectors in a basis for the given space. So given this n of t, the null space, suppose that the dimension of the null space is k, meaning we can find some basis for the null space, and this basis will contain k vectors. Okay? Now, of course, this k will be less than or equal to n, and we learned a theorem previously that given, oh, first of all, this is a basis. A basis of n of t. Then basis means it is independent, and it can it will span the n of t, right? These two requirements are satisfied. So this is a basis, meaning, as I said, this is independent. So if I have some independent set, previously we considered one theorem saying that we can expand that independent vectors to form a basis, meaning this set of independent vectors can be expanded so that the span will be the same as the whole space. So we can add some vectors. So we can add some vectors to this basis to form a basis for the whole space V. So when we may extend, that means, so here let me consider this. So I have V space and I have n of t. And within this n of t, I can find v1 up to vk, and they form a basis. And I know that they are independent because they are independent basis. Then given this basis as vectors in V space, okay, so this beta is a set of vectors in V space. I can extend, right? If the dimension of V is n, then I require n minus k vectors. So there will be V k plus 1 up to Vn, so that you have n minus k vectors outside of the null space, right? They cannot be inside of n of t, because in that case, the dimension will not be k. So we can find those n minus k vectors so that this v1 up to vk and the extension v sub k plus 1 up to vn will be a basis for V space. We can extend this, meaning we can find those n minus k vectors outside of n of t to define a basis for the whole space V. So that's what you can do. So we can find. Oh, sorry. This is not beta, and this is beta. Sorry about that. So let me call this guy as the beta one. Then this beta one is still beta one is a basis of n over t, and this beta one is independent. So I can extend, meaning I can find these n minus k vectors to form a basis for V space. So that's what I did. Okay, I just introduced those n minus k vectors, and beta will be a basis for the full space, right? We can always find those n minus k vectors, right? Now we want to prove that the images of v sub k plus 1 up to v sub n, they form a basis for the range. So that is the claim here. So this set will form a basis for all of t. Now first, let us prove that S generates, so this set is called S, and this S will generate all of t because all of t is, okay, beta is a basis, so t of beta will generate the range. So range is generated by span of t of beta. So this is t of beta, right? That's what I just mentioned. Now, in this t of beta, t of v1 is 0 because v1 is a vector in the null space. v2 is also mapped to 0. So, given this t of beta, t of v1 up to t of vk will be all zeros, right? And they do not contribute anything but 0. So when I generate, in other words, when I consider the span, the contribution from t of v1 up to t of vk can be neglected. So I can discard those k vectors, right? So please remember that span of t of v1 up to t of vn, that is the collection of all the linear combinations of these n vectors. Say c1 t of v1 up to ck t of vk, ck plus 1 t of vk plus 1 up to cn t of vn. So the span of these n vectors is the collection of such vectors. Now, in this expression, t of v1, t of v2 up to t of vk, they are all zeros. So this is a 0, this is a 0. So this expression will be 0. So what remains is just a linear combination of t of vk plus 1 up to t of vn. In other words, they will generate the range. Okay, so S generates the range. Now, as I said, when I proved the previous theorem, at this point, t of vk plus 1 up to t of vn may be linearly dependent, right? We do not know. Now, right? I mean, how can I check whether they are linearly independent? If they are not independent, so that if they are linearly dependent, then the dimension of the range will be less than n minus k. Then how can I prove that those n minus k vectors are linearly independent? Excuse me. Okay. Now, to prove that this is S is linearly independent, let us consider an arbitrary linear combination of those vectors in S, and then let me assume that this linear combination is 0. Okay, so let me assume this one. So suppose that we have this equation for some numbers. Since t is linear, the previous equation can be written by this. T of these vectors, t of this vector is 0. What does that mean? This vector is mapped to 0. In other words, this vector is a vector in the null space. If it is a vector in the null space, what was the basis of this n of t? It is the basis was v1 up to vk. So if I have any vector in that space, that vector can be written as a linear combination of v1 up to vk, right? So that means this vector can be written as a linear combination of v1 up to vk. Okay, right? So that means we can find some numbers such that this equation is satisfied. Now, let me move this term to the other side. Then we have the sum of this will be 0. Now, what does that mean? I have v1 up to vk. For those k vectors, negative c1 up to negative ck are multiplied and added. And for v sub k plus 1 up to vn, b sub k plus 1 up to b sub n are multiplied, and this whole linear combination will be 0. But what are these vectors? v1, v2, vk up to vn. These vectors are a basis for the domain. That's how we defined v sub k plus 1 up to v sub n, right? We initially had these k vectors for the null space. That was a basis for the null space. And then we extended, right? So that these n vectors will form a basis for the domain V, meaning they are linearly independent. These are linearly, basis means they are independent. If a linear combination of those independent vectors is 0, then the corresponding coefficients must be zeros. That was the property or definition of independent vectors. So, if I have this linear combination of basis vectors is 0, then all the coefficients, negative c1 up to negative ck and b sub k plus 1 up to b sub n, they are all zeros. So, especially these b sub i's are all zeros. So, what did I obtain? I assumed that some linear combination of these t sub vi is 0. Then what was the conclusion? Bi's are just the zeros. Then what does that mean? This implies that these t of vi's are linearly independent. So that means this set is linearly independent. Oops. Yeah. So this set will be a, so S is linearly independent. So 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 let me go back to this. Our S was this set. Okay. S is a S is linearly independent, and S generates the range. So it is a basis, right? So the dimension of the range will be n minus k because the basis has contains n minus k vectors, right? So given any linear mapping, the nullity plus the rank will be the dimension of the domain. Please remember, this is a very useful theorem. Uh, so, so let me go back to the previous example we considered. In this example, this T is a linear mapping. What is the the dimension of the range? Dimension of the range is 2. So that is the rank. What was the nullity? Dimension of the null space is 1. So that is the nullity. Nullity is 1. Nullity is 1. Rank is 2. What is the dimension of the domain? P sub 2 dimension is 3 because it's one of the bases is this standard basis and it contains 3. So that means the dimension of the basis and the domain is 3. And this result is not coincident. I mean, okay? I mean, so this dimension of the domain is the sum of the dimension of the rank, the range, and plus the dimension of the null space. So by looking at this basis for the range, you should be able to imagine, I mean, derive the fact that the nullity will be 1. Okay. Okay, now functions such that each element of the range has a unique preimage are called one-to-one function. So in other words, a function f from a to b is one-to-one if f of x equals f of y implies that x and y are equal. In other words, if you select any two different vectors from the domain, their images will be different. So if one of these two is satisfied, then the function will be mapped to one. So in elementary school days, we considered some diagram like say A, B, C, and 1, 2, 3, 4. Then any mapping like this is called a one-to-one mapping. So that is one-to-one. Now, if a range and codomain are equal, then we say the mapping is onto. Okay. So if the range and codomain are equal, then we say the mapping is onto, right? In other words, in other words, if you choose any vector in B is on image of some x in A. Okay? It is an image of something. there may be multiple vectors in A whose images are all Y, right? That may happen, but anyway, as long as f of A equals B, in other words, the range and codomain are equal, then the mapping will be called onto. And given a function f from A to B, and when S is any subset, sometimes we can define a function from S to B, okay, when eh, when for any x in S, the image of f sub s of x is f of x. In that case, we say this f sub s is called the restriction of f to s. Okay, so for example, if is this example is considered, okay, this let me consider this f, then when I restrict S to a subset of A, say the set of A and B, and if I define, then f sub s, this restriction will map A to 1, which is f of 1, and B is mapped to 2, which is the image of 2 under f. Then, so this f sub s is a mapping from S to B. We can consider this function f sub s, and this f sub s will be called the restriction of f to s. So that is the terminology. Now in theorem 2.4, suppose that V and W are vector spaces and T is a linear mapping. Then, moments ago I considered a one-to-one mapping. My T will be one-to-one if and only if null space contains 0. This is theorem 2.4. I will check this, get back to this 2.4 a few times throughout the semester. So this theorem is very simple but strong, powerful. T is one-to-one if and only if the null space contains only 0. So to prove this, let me first assume that T is a one-to-one mapping. Okay, and let me choose an arbitrary vector from the null space. Now, since x is chosen from the null space, by definition of the null space, the image of x will be 0. And I know that 0 is the image of T of 0. So T of 0 and T of x are the same, right? So here T of x and T of 0 are the same. They are equal. Now, what was the definition of a one-to-one mapping? We say the mapping is one-to-one if the equal image implies equal pre-image. So when T of x and T of 0 are the same, and if I know that this mapping is one-to-one, then x must be 0. Meaning, when I select any arbitrary element from the null space, that element must be 0. In other words, the null space consists of only 0 vector. So when I assume the left-hand side, okay, so when I assume the left-hand side, I derived the right-hand side. Now let me assume the right-hand side. So let me assume that the null space consists of only 0. And to prove that this mapping is one-to-one, let me assume that t of x and t of y are equal for some x and y. If I can show that x and y are equal, then this mapping will be a one-to-one mapping, right? Now, since the t of x and t of y are equal, t of x minus the t of y will be definitely 0. But since the t is a linear mapping, I can consider this a subtraction in the domain, and then you can apply t mapping. That was one of the property of the linear mapping. So that means x of y is mapped to 0. So x minus y is mapped to 0. So x minus y must be included in the null space. So x minus y must be included in the null space. But the only element in the null space is 0. So x minus y must be that 0. In other words, x and y must be equal. So if I assume that the null space is the 0 space, then this mapping must be one-to-one. So this is a very important property. So to prove, to validate a mapping is one-to-one, I need to show that the null space is the 0 space. Now let us consider the theorem 2.5. So suppose that I have finite dimensional vector spaces V and W, okay? And let me assume that the dimension of the domain and the dimension of the codomain are equal. So I will assume that this V and W have the equal dimension. Then, then following three statements are equivalent. What does it say? The first statement says the mapping is one-to-one. The second statement says the mapping is onto. The third statement says the rank will be the same as the dimension of the domain. Well, from the dimension theorem, we have this. So, if the mapping is one-to-one, this is equivalent to saying the null space of T is the 0 space. That is equivalent to saying that the dimension of the null space is 0, and that dimension is called the nullity. So T is one-to-one. Statement A is equivalent to saying, so that is equivalent to saying that the nullity is 0. Now, since we have the dimension theorem, if the nullity of T is 0, then rank and the dimension of the domain must be the same. So if A is true, then C will be true. And if C is true, then the nullity of T must be 0 from the dimension theorem, and the mapping must be one-to-one. So A and C are equivalent, as you can see, right? So if the dimension, so so A and C are equivalent, okay, in any situation, right? I don't need this equal dimension between the V and W. For any vector space V and W, and if the mapping T is linear, then that linear mapping will be one-to-one if and only if the null space consists of 0, so that the nullity is 0. Okay? You understand what I'm saying? So for any V and W and T from V to W. Okay. The T is one to one. This is a notation for one to one mapping. That is equivalent to saying that the null space of T consists of 0. That is equivalent to saying that the nullity is 0. And since we have this strong formula, the demand, okay, the sum of the nullity and the rank is the dimension of the domain. If the rank, if the nullity is 0, then that means rank of T equals the dimension of V space. So this is true in any situation, in any situation. Now, in this theorem, I have one more condition saying the dimension of the domain and the dimension of the codomain are equal. Then we can also consider this second one. Why? The nullity is 0, so the rank is T. What is the rank? What is the rank? If this is the case, then what is the rank? Rank is the dimension of the range. And what was the assumption? Dimension of the domain and dimension of the codomain are equal. Oops, I'm sorry. Sorry. No, not this one. The rank of, yeah, this one. Rank of T is, oops, no. So the point is, okay, so this is what I'm, not what I'm telling you. So if your mapping is one to one, so that the rank equals the dimension of V, rank is the dimension of the range. Okay. And what is the assumption here? Dimension of the range equals dimension of V, which is dimension of W space. So if your mapping is one to one, the dimension of the range and dimension of W are equal, so that all of T and W are equal. And vice versa. If the all of T and W are equal, their dimensions will be the same, so that rank, dimension of W, dimension of V, they all must be the same, so that the mapping must be one to one. So in general, we have this. But in general, one-to-one mapping may not imply onto, or onto does not may not imply one-to-one in general. But if the dimension of the domain and if the dimension of the codomain are equal, then one implies the other. One-to-one, being one-to-one implies being onto, and being onto implies being one-to-one. This is a very powerful statement, and I will use this theorem later for the solutions of system of equations. Now, let us consider some examples. Suppose that we have a linear transformation, linear mapping T from P2 to P3, which maps F to 2 times F prime plus this integration. Okay. Now, the range will be spanned by the images of the basis of the domain. And for P2 space, we have the standard basis of 1x and x squared. So their images will span the range. For t of 1, 2 times the derivative of this constant function plus 3 is integrated from 0 to x. So the first term is a 0, and when 3 is integrated from 0 to x, you get 3x. In case of x, if you differentiate x, you get 1. And then if you integrate t, 3t from 0 to x, then you get 2 times of 1 plus 3 half t squared is evaluated at 0 and x, and right, and then you consider the difference, then you get 2 plus 3 half x squared. This one is obtained. And then if you consider x squared, you will get 4x plus x cubed. Now, are they linearly independent? Yes. You can easily check that they are linearly independent. So the dimension of the RT is 3. In other words, the rank is 3. Now, what was the dimension of P2 space? Dimension of P2 is 3. So the dimension of the range and dimension of the P O N, okay, okay. But the problem here is this: the rank and dimension of P2, the domain, are the same. Then is it one to one, and or is it on to? Well, what is the dimension of the codomain? Dimension of P3 is not 3 but 4. So dimension of the codomain is different from the dimension of the domain. So we cannot think of the previous theorem. Okay? So this mapping is not onto. Okay? But if the rank is 3 and the dimension is 3, the dimension of the domain is 3, then, as I said, rank and the domain, if they have the same values, then nullity will be always 0. So the mapping will be always 1 to 1. So this mapping will be always 1 to 1. Even though I do not know the calculus in detail, but the null space will be the zero space only, okay? And the mapping will be 1 to 1. And that comes from the dimension theorem. Okay, I mean the sum of rank and the nullity is the dimension of the domain. So from that theorem, I can prove that this mapping is one-to-one mapping. Actually, showing one-to-one is quite complicated for this technique, the calculus problem. But if I borrow this theorem from the linear algebra, we can easily prove that statement. Example 12. So suppose that I have a mapping T from F2 to F2 and A1, A2 pair is mapped to this. Now, in this case, dimension of the domain and the dimension of the codomain are the same. Dimension of F2 is the same as dimension of the codomain F2. And what is the null space? So A1, A2 pair is in the null space, meaning the image A1 plus A2 is a 0 and A1 is a 0. If A1 is a 0, when I plug in this value to the first equation, A2 will be also 0. So that means A1, A2 pair is in the null space. That is equivalent to saying that A1, A2 must be the 0 vector, meaning the null space consists of only 0 vector in F2 space. Okay, so since in this case the dimension of the domain and codomain are the same, this implies that the mapping T is 1 to 1. So in this case, I can derive that my T will be onto mapping. Now, this is just extract the obtained from the exercise of the textbook. So please read this, okay, and please check, especially B and C, okay. And actually, I already proved in the class, but you need to check this one more time. Now let's consider example 13. So T is a mapping from P2 to R3 space. And note that P2 is a three-dimensional space, R3 is a three-dimensional space. Okay? So, and T is mapped from this polynomial to A0, A1, A2. Now, is it one-to-one? Yes. Why? Because if I assume that this A0 plus A1x plus A2x squared in the null space of T, that will imply that A0, A1, A2 triple must be the zero vector. Then that means A0 is 0, A1x is 0, A2x squared is 0. I mean, this is zero vector. So that means the null space contains only 0, right? So the mapping will be 1 to 1. It is 1 to 1, and the dimension of the domain and dimension of the codomain are the same. Dimension of P2 and dimension of R3, they are both 3. So if your linear mapping is 1 to 1, it will be onto as well. Okay. Now, in addition, if I consider some S in P2 space, you can easily show that they are independent because the images are linearly independent. Is it true? Do you understand why this portion becomes the reason of this statement? S is independent because T of S is independent. Why is this lower part on a reason for the statement above? Why is it so? So please think about it. Okay. So if you're not sure, then you need to think a little bit. It is clear, it is straightforward, but you need to check. You need to ask yourself, okay? You need to ask yourself that this lower part is actually a reason explaining this upper part. So please check whether yourself knows this or understands this. Okay? So please think about it. And if you have any questions, please email me. Okay? And if you have any doubts, you can watch the video lecture one more time on the YouTube. I will upload in an hour or two. Okay? Thank you for listening and see you next time.